Okay, Assalamualaikum warahmatullahi wabarakatuh. So we're going to continue with the DC drive. We have talked about the part one of the DC drive last 2 weeks. Okay, so we're going to continue into part two. Inshallah, we're going to finish the DC drive just after the semester break, right? Okay, so we have talked about the DC motor drive. We look into the principal operation. By the way, I have share with you a uh, new file. I can go to the folder, right? There is a new file for you which is under the name of drive 01. So I replaced the last one that you shared with you. So this is a new file, and then this is going to be the notes for today's slides, right? Presentation. Right, and also I've also shared with you the simulation, the installer for the PSIM. We're going to use a PSIM for the simulation. Remember, we have CO3, which is actually cost outcome number 3. Will actually teach you or share with you how to simulate, how to use the modern tools to simulate the DC drive or the electric drive. Right, so we start with the PSIM. I don't know whether you have used the PSIM before in Powertronics, or probably you use a MATLAB, but inshallah I'm going to start with the PSIM, and inshallah we have a look and whether I can use a MATLAB Simulink or PSIM, right? Either PSIM or MATLAB Simulink. And then I share with you the one example. Please try yourself, make your own circuit, right? So this is a DC motor, right? So this is a DC motor under two conditions. You have two conditions here. With this, okay, so we have two conditions. One is a constant torque. We're going to look at what is a constant torque and also the constant power control. Okay, so this is your machine, and then you need to connect to your considering this is a separately excited DC motor, so you have a different field winding. So this is your field winding, and that is your motor, armature current, armature circuit there. Okay, so please watch. I'll also share with you. I'm going to share with you how to uh, the explanation on how to use the PSIM here, how to locate that in the YouTube. Please go there and try to simulate yourself. Right? Okay, so this is simulation, and again we have new materials which is under we have 01 and part 2 02. So if you look at the part 1, the new file consists of a new slide. I put in some slide here. This motor introduction, and then some revision on Lorentz force. What's the Lorentz force? So you have to use a left hand rule, right hand rule. So that is the two rules. I mean, the rules are the force that, that rotate these machines. Okay, and then we have this keeping the force unidirectional with commutators, because it's a DC motor. You need to have a DC voltage, and this is how it used in this machine, so that you can have a unidirectional force in the machine. Okay, and then we have a construction, the basic construction of the DC motor. So you can zoom and look at how the arrangement of the windings around armature winding, and we have a commutating, uh, compensating winding. Okay, so this is actually you have learned this in electrical motor in part 4, if I'm not mistaken. Right? then the operation, and the classification of what is a separate sighted series motor and compound motors. Okay, how it is connected, the equation, okay, series motor and the applications, some basic theories of operation, what is a torque developed, and the voltage developed, Faraday law, and as well as a left hand rule. And then we have this basic uh, speed control DC motor, and it is based on the separately excited. We start with a separately excited shunt motor, and this is the key equation, the important equation that you need to look at. And this, from this equation, you can control the speed by varying some of the few variables here. For example, you can vary the speed, the terminal voltage, you can carry the armature resistance, and you can also vary the field, the flux in the field winding, so that you control your speed. Our purpose is to control the speed. So this is the parameter that you can change, so that you can change the speed. Okay, so there are three, based on that equation, there are three probability of three options that you can do to control the speed. The first one, resistance in armature circuit, the terminal voltage VT, and finally the field flux. And this is the key equation, key component that you can change to change the speed. So we have looked into the examples of three of these, and also the key equation in the three controls here. Alright, we have gone through the examples, some solution. So I did share with you the solution in the notes. Right, so just go through again, look at the answers there. And we will look into the torque speed characteristic. This is a speed torque characteristic with armature voltage. We also have a adjusting resistance, armature resistance, armature voltage, and field voltage. And finally, we go to the adjusting field voltage. Is that it? Yeah, so you just go back and look at the notes again. So now, the notes that I've shared now is actually consists of the solution compared to the previous one. Okay, so now we go through the solid state control. So remember, we have three types of control. The first one is the controlling the armature resistance. But however, that armature resistance is not an efficient way to do. It's a very inefficient method because we when we put the inserted the resistance in the circuit, it actually can cause you a loss, right? And also a heating, it becomes a heat, and it is a loss. And the use of resistance is acceptable only when the resistance is used for a very short period of time. So if you want to change the speed at just a short period of time, then you can apply this armature resistance, or else you will experience a different situation. For example, uh, the high losses, right, because of the additional resistance. Therefore, what left is only the terminal voltage control and the field flux control by means of controlling the field voltage, right, as well as the current, how to control that. We control the uh, field voltage as well as the uh, terminal or armature voltage. So this is two methods that we're going to look at. So how to change the voltage? Uh, so there's another note here. The greatest advantage of using is the variable speed characteristic. Yes, because you can adjust the speed. Although the ability to change motor speed is often desirable, it is generally necessary that the motor maintain a constant speed once it has been set. So if you drop, for example, you want to drop the speed from 1800 to 1200, then what you do is you send, this is a sort of a block diagram of the system. So what you need to have is you send a signals to the operator control here, so you will produce a some we call it control elements in the phase shift control here, so it will change the behavior of the rectifier, the operation of the rectifier. Therefore, you will change the DC voltage. You will see the DC voltage across the nodes here, and therefore you can change the speed of the motor here, right? So therefore we need to have a solid state control. We call it a solid state control, and that is of that. So rectifier plus the phase shift control is known as a solid state control. You use a circuit to control the rectifier. Okay, right. Next, before we proceed, I did mention about the torque speed, the constant torque, as well as the constant power. So uh, we need to know that we only can increase the VT. Remember, we have VT here, right? We can only increase that up to the rated voltage, up to the rated voltage, which is we rated this. Okay, so you have each of the machine has its own rated version, rated voltage, as well as the current. So you can only increase. Okay, you can only increase. You can only increase the voltage here. Okay, wait. Okay, so we have this V rating. VT has its own V rated. Okay, the maximum voltage that you can handle. So you can only increase the voltage up to the rated or maximum voltage here. Right? So once you reach that speed, this is known as base speed. So when you operate at V rated, okay, this is known as a base speed. Okay, so from there you have a base speed here. So from zero speed up to that particular V base, the the omega base or base speed, you can increase the voltage or reduce the voltage. You can increase or reduce the voltage, and we can also at the that uh, operation, while we have this operation, we usually have a constant torque there, right? We have a constant torque operations there. Okay, but next, when you start to go, if you want to go beyond that omega base, which means you want to increase further, the speed should be greater than the omega base. Now you have what you need to do is you have to reduce the flux here, isn't it? Yeah? So if you reduce the flux, then you actually increase this particular uh, omega naught here, isn't it? This is no load torque equals to 0, isn't it? So we have omega naught. Last week we talked about this. So what is omega naught? Isn't it? Uh, no load speed. So when you reduce this flux, then this term will increase. Therefore, you can increase. So while you're doing that, when you increase the omega, the torque will reduce because you have to have the constant power operation. So you can only increase the speed of the motor beyond the base speed by using this controlling method, which is sometimes known as a field weakening. Field weakening, so which means you reduce the flux by means of reducing the IF, because we know that the flux is proportional to IF, the field current here, right? So this is what is known as a base speed, field awakening, torque constant, and this is the power constant. So that is why we have this in the simulation just now. I have this constant torque voltage as well as constant power field awakening control. So you can have a different. This is mechanical load, right? If you look at the elements, go to power, there is a mechanical load and sensor. So you can have a few options. If you want to have a constant torque, then you use this mechanical load. If you want to have a constant power, then use the mechanical load here. So there are two different load. So in this constant torque voltage control, we maintain the flux. Okay, we maintain the flux, but we can reduce and increase the VT here. Okay, so if I can run this circuit, transmission, I want to remove N2 first. I want to remove the IF first. Okay, so look at that. The IF, which is the flux current, the field current, is 1.6, which is the rating current. And then if you look at the speed, now it reached 1200 RPM. So this is required RPM with the 120 volts. So we just look into the constant torque operation there. The constant torque operation. So this is the operation of 120 volts. So what if I reduce this terminal voltage? Now it is 120. So let's see. I'm going to reduce that to 60 voltage. 60 volt. Run again. Simulation. Now I get roughly about 620 RPM, which is about half of the 1200 RPM just now. Okay, so this constant torque, then you can try for the constant power here by means of changing this value. Okay, so if you change the value, you actually change the current, and therefore you reduce or increase the flux. Okay, so that is the solution. Have a try. Okay, look at one by one all the examples here. It's very good to have the PC simulation. Okay, so that's a PC. Let's close that. Okay, and now look at the solid state control. It's used for enhanced efficiency and for versatile operation of electric drive. For DC machine, converters are used in the armature circuit to control the terminal voltage of the motor. In some cases, the converter is also used to control the field voltage. When a converter is used, the power source can be either AC or DC, which makes the installation of the machine independent. So we're going to discuss the two techniques or two circuits that involve in the DC drive. It can be from a DC source, it can be from the AC source. Okay, so we're going to look at the circuits, also how to control this motor by using these two conditions, whereby the supply is only DC or AC. Okay, next, solid state control, controller rectifier in this case. So have a look at here. We have the front. We have the supply is in terms of AC supply. Okay, so we have a control rectifier, so that will convert AC to DC, so that DC will be connected to your machines. And here you have a control rectifier. You can have a straight solid converter to do that by means of control rectifier. And then for the field windings, just enough to use the diode bridge to control the IF, also VF here. Okay, so that is a control rectifier. Then you can also have a DC-DC converter. So if you look at this, it should be from DC to DC. So that's it. So we have, let's assume that we have a input is a DC. So we just apply this DC-DC converter to control the speed of your motor. Hmm? So that is known as a DC-DC converter fat drive. So in the front end, just before your motor here, we have a DC-DC converter. In contrast, for the control rectifier, before the machine, we have this AC-DC control rectifier. Okay, so just to remind you again on the 4-quadrant operation, this 4-quadrant operation is very important if you want to control if you want to apply this drive to understand the drive operation. So just remember, we can have omega torque characteristic. Remember, we can also have torque speed characteristic, okay, which is the invert, isn't it? It interchange from y-axis to x-axis. You can represent this in terms of that, okay, torque versus speed, or you can have speed versus torque. But the reference for the region is always the same. So you have the first one is first quadrant, and then the second one for the omega versus torque, we have this from the if you use a counterclockwise direction, from 1 you see the 2, and then 3, and then 4. Okay, right. So if you change the torque and speed, so it still remain the same 1, then you have 2 here. Okay, so it still maintain the number 2 here. Right. So this is condition of positive speed. If you look closely, this is where you have a positive speed, and for the other two you have the if you talk about this uh, uh, this is call it first quadrant and second, we have a positive speed. So the speed only uh, follow the counterclockwise direction. Okay. So here we have a negative speed, and that is for the current quadrant 3 and quadrant 4. Okay, and later on we're going to see also the quadrant actually defined by voltage and current. And the voltage across of the terminal voltage here, as well as the armature current. We can also have that uh, characteristic, or the quadrant is always referred to that 1, 2, 3, 4. 1, 2, 3, 4, and for this torque versus speed, it goes 1, 2, 3, 4 there. Okay, right. So next, solid state control. Again, this is the, you can refer to Rashid's book. If you can find a PDF, go and find a PDF. If not, go and look into the library. Right, Harun Rashid. His name is Harun Rashid. So if you talk about edition 4, this is the 4th edition. Alright, so it should be on page 702. Rashid 702. So if you go there, then you can find this equation. Okay, so here it shows that this is your field circuit, then you have the armature circuit connected to the load. Right, so therefore the developed torque can be some constant KT multiplied by IF multiplied by IA, because we also know that torque, okay, we also know that torque is also equals to K flux IA. Is it? So flux is the I F, and therefore you have torque equals to K IF. Okay, so you have this equation, and also you have this KT flux IA. Okay, for normal operation, the developed torque must be equal to the load torque. So we have this. The developed torque equals to TD. This is the moment initial of the motor, but it multiplied by d omega over dt. Then you have b omega, and finally the load torque. Okay, so the combination of three of that, the total torque from inertia, from the friction as well as the load torque, must equals to the developed torque by the machines. And if you want to move your machine, then you have to make sure that it is equal. They are equal. Okay, right. Field and armature winding. So if you look at the field winding equation, will be VF RF IA. VF equals to RF IF plus LF DIF over dt. So if I may come back here, so this is circuit. So you have VF equals to IF and or it can be IF plus RF, and also we have DIL over dt. LF multiplied by DIL over dt. Okay, so that's why you have this equation here. Okay, and then we have instantaneous armature current VA equals to RA IA plus LA DIA over dt plus EG. And then the motor back EMF, also we know that EG equals to KV omega IF, or you can also write the equation of E. Equation of EG or E back EMF equals to K flux omega M. K flux omega M or omega, and again flux is proportional to IF, and that's why you have this equation on the left hand side here. Okay, so that's why you have that equation. Okay, nothing new. So under steady state operation, so we have to know that under steady state operation, if you may write or may sketch the omega, you do this. So this is your omega. Therefore, if you talk about the derivative of the parameters, for example, d omega over dt, so what does it mean? The rate of change, isn't it? The rate of change over the time. So if you look at this particular region where it's already reached, where it is already reached the steady state, now we see that there is no change of W over dt, which is there's no slope, isn't it? There's no slope, and therefore it is zero term. So this is become zero. So that's why there's no longer, if you look carefully, if you talk about question, there is a LF DIF over dt, you have LIA over dt, isn't it? So if you do that in terms of under steady state operation, so what left is only VF, IF, RF. So you just take the voltage drop across your R. So you forget the inductor because of the steady state operation. The time derivatives are zero. And then that also goes to the VA, the armature circuit, equals to RA, IA plus EG. And then if you replace, then you get KV omega IF. Okay, go further. Under states condition, the time derivatives in this equation are zero. The same remarks. So this is the equation again, VA equals to RAIA plus EG, RAIA plus KV omega IF. And then we have TD equals to KT IFIA also, and also we have this BT or omega plus KL, TL. Okay, so that's the equation. The developed power is, of course, we know that the developed power is one spot power equals to omega top. Speed of excited motor can be found from. So there are many equations to write the omega. So this is in terms of IF or RF. So just now we have in terms of flux, further. Equivalent circuit of DC series. So now we look into the DC. So this is a key equation of the separately excited. So we talk about a DC series motor, the same uh, drawing here. So you have a friction, and then we have this torque torque, and then we have this again, the armature. They put it together because you're in series. So you have the LARA, also LF, RF. Okay, so just write the steady state average equation. So we have EG equals to KV. So just read that, it's straightforward. It's an average equation, KVL, and that's what you have. So the speed of a series motor can be determined by this value now. If you replace, then you find out that omega equals to VA minus RA plus RF multiplied by IA divided by KVIF. So that is a series motor. Next is to look into the schematic for a gearbox between motor and load. So normally we use the gear to transfer the energy to actually increase the speed or reduce the speed. You can have this gearbox whereby you have a ratio here to determine the speed of your motor, N1 over N2 there. Is it? Okay, schematic for gearbox between motor and load. And the gear, okay, assuming zero losses in the gearbox, the power handled by the gear is the same on both sides. So both sides you have the same power. So power equals to omega torque. Therefore, omega 1 torque 1 equals to omega 2 torque 2. The speed on each side is inversely proportional. So if you look closely, you can actually trace and get that equation. Omega 1 over omega 2 equals to N2 divided by N1. Okay, so you can use power equation. Okay. And you have that equation here, T2 equals to N2 over N1. So which means similar to a transfer, the load initial J1 and the load bearing towards the V1 can be reflected to the motor side. So which means in this circuit, you can also actually transfer this from the second gear here to this side from the gearbox. You can actually refer all of this to the front end, and therefore you can apply this equation here. So Jm, the total inertia that we face on the left hand side there, on the top side there, equals to Jm N1 over N2 squared J1. So which means you bring the J1 into the original circuit on the left. Okay, so you transfer all of this term to the primary side, for you to calculate the total top equation there. Okay, so now we're going to look at the I did mention that we can have a AC input, or can also have a DC input is it AC or DC. So we start with the AC input, right? So we have this rectifier. We're going to look at what is half wave drive and full wave drive, and also what is the effect of freewheeling current or diode that will be added into your circuit. Okay, so we have three. And next, we're going to look into the chopper or DC. In the next class, we're going to look at the chopper, whereby we use the DC to DC as the converter there. Okay, so let's look at this. Basic circuit arrangement for single phase DC drive. I hope you also can look into the Rashid's book. Harun Rashid. It's a very good book also for the drive. Harun Rashid. Right. So This is very much the basic arrangement of single phase. So you have a AC supply in the front end there, and then you have this control rectifier. You can have a single phase, half wave or full wave control rectifier. And on the field winding, we can have this again, the similar circuit here, or you can have a diode bridge for the field winding if you don't want to vary the voltage for the field winding. Okay, but if you want to vary, then you might have the two control rectifier for the field winding and as well as the armature winding. Right, so basic configuration of DC motor with a converter. So this is source converter, and then we have a motor, and then we also have this field rectifier. The armature circuit of the circuit is connected to the converter, which fed from an AC source. The field circuit of the motor is excited from the AC source through a rectifier which may contain filters. Next, okay, we look first on the single phase half wave drive, whereby we use the half wave. This is half wave rectifier, isn't it? A single thyristor is used, then we can have that um, waveform here. So this is your back EMF. Right, so back EMF is having this voltage, right? So this is EA. Let's say this is EA. So that is your EA with a straight line, which is represent the back EMF in the circuit, and therefore, and this is your supply current, the supply voltage there, which is the dotted line there. This is the supply voltage, the sinusoidal supply voltage, and therefore then you start to trigger the thyristor here at alpha, isn't it? So we have alpha there. So that's alpha. Okay, you can only trigger alpha when your voltage here, so your Vs should be greater than EA. Right? Then you can your alpha here should be greater than that point. If I can mark that point, so you must have this. Let's say this is alpha naught, right? So alpha should be greater than alpha naught. Okay, should be greater than alpha naught. If not, your thyristor will not be turned on. Okay, why? Because if EA is greater than Vs, your current is actually will flow into that. Isn't it? Yeah. So this is actually on. You can't turn on the, I mean the thyristor because it is in reverse bias. So you must be sure that it's forward bias. Then get it. So that forward bias only happens when you have alpha greater than that point. So when you start to trigger alpha, before you trigger alpha, what happens is that what happens to the thyristor? It is turned off, isn't it? This is open circuit. This is open circuit. So there is no current flow. EA equals to 0, isn't it? So there is no voltage drop here. There is no voltage drop there, and therefore EA, if you measure that point, this is, sorry, if you measure that point, so this is V out, so this is V, in this case, so VT here, let's say this is VT, so the VT equals to EA, isn't it? VT equals to EA because before you turn on the thyristor, it is off, there is no current flow, therefore EA VT equals to EA. So that's why from there, from the beginning until there, you have VT equals to EA. But once you start to trigger the thyristor, this is switched on, and therefore Vt will be equals to Is. Yeah? So Vt equals to, sorry, Vs. That's why it will, from there on, it will copy the input voltage until it goes to negative half cycle. When it goes to the negative half cycles here, the thyristor will stay. Because of that inductor here, current still flow in that direction even though Vs is negative. So we change to negative side. Okay, this is negative half cycle, so already goes to negative. However, because of that inductor, current still flow in that direction, and therefore it's still on until Ia equals to 0. So at this point, then you can see the current equals to 0. At this point B, this is known as extinction angle, isn't it? You can refer to Powertronic book, Powertronic notes last semester. Then it's equals to beta is extinction angle. Extinction because Ia equals to 0. So this is the point, current goes to 0. So when the current goes to 0, then it goes back to the previous condition whereby Vt equals to Ea. Right? And that's why you have that Vt there. Okay. So this is actually in the Powertronic notes. You can I'll probably share with you the monograph that I had, right? For you to look into the, just to get some revision on the Powertronics. Okay, so and therefore um, if you get the V out, right, it's always 1 over T. You integrate the average of the, you integrate the whole Vt equals to Dt0. So you integrate the whole cycles, one cycles, and then you divide by IT. So this is the area under the curve. So you can actually start from there until there, and then you end. This will be your one cycle, one complete cycle. So your T is actually from there to there. You can start from there to there. Right? So you integrate from there to there. So you need to find what is the output voltage, that area, the small including output this area, and that area as well. Then you have to divide by T. You have to divide by T, and finally you get this equation here. Okay, so this is your Vt. Right, so Vt equals to Vmax or V peak. Sometimes I usually use the V with a hat. So V peak, you divide by 2 pi cos alpha minus cos beta. And this is from the notes. I'm going to give you the equation again. Right, so you have that Ra. So if you look into the Sharkawi book, page 166 will explain you how to do derivation. 166. There you are. Okay, so it integrate. Get it further. So it integrate from, this is a current equation, and that is your derivation to get the voltage. Okay. So you have EA, RA equal to 2 over pi, I squared pi. EA plus, this is a equation just now, this equation, and then this is the average current. Simple and average current there, so it just changed to IAV. or if you cross multiply everything, then you have all this gone. RA over 2 pi. Okay. Right, and finally you have this equation. That equation. Right, Vmax over 2 pi cos alpha. So what is a this is called gamma. Gamma is the conduction period. Yeah? The conduction period is actually from this describe the conduction period from there to there. Beta minus alpha. So this is your gamma. What is the angle there? Beta minus alpha. Then gamma. Okay, so that will be your equation. Okay, so we will look into the equation. Some example on that, inshallah. Okay, so next, now we talk about single phase full wave drive. Full wave drive. So in this case, you can have the switching of the series independent. So if you look at this single phase half wave, it can only work on the single quadrant. Okay, so this is known as a single quadrant operation. So it's only work from that condition. Quadrant 1, whereby you have omega on top, or you can also use the voltage. Okay, voltage against current. You can also do that. Right, so this is condition 1. It can only operate that because the current always flow in that direction, and the voltage also only that direction. Yeah? That VT here is always that direction, plus minus there. So you can only have one quadrant operation. But if you talk about full wave, okay, full wave, or sometimes, I mean, normally it will be presented in terms of it will be draw in terms of that connection, isn't it? This is rather common drawing of full wave. RA, LA, okay. So your current flow through here, and this is thyristors, all thyristors. So you can control the turn on, the delay angle or turn on, so that you can control the voltage across this. So this is your VT, again your back EMF, EA. Okay, right. So right, so in this case, you can have positive of the voltage source, positive and negative half cycle. The switching can be polarity of the switching will say is dependent. So normally you're going to have S1, so here you have S2, S3, S4, for example. Right? So this yes, they are right. So you normally will have the same signal for both diagonal switches here. So S1 and S2 will receive the same similar signal, and S3 will operate as the same as S4. So alpha should be a applied to S1 and S2, and we also have alpha plus pi for S3 and S4. Okay, so alpha S1, S2, and for S3 and S4 you have alpha plus pi. Why? If I may write this. Okay, so you want trigger alpha here, and this should be alpha plus pi 3. So during positive half cycle, S1 and S2 will be turned on. Therefore, the voltage will follow this direction. This is a purely resistive load, pure resistive load. So you go there and then stop. Sorry. Then you have this voltage for S3 and S4. When this S3 and S4 on, the output voltage. This is only for purely resistive load. Okay, we consider a purely resistive load, so this is your output voltage that you receive at the output. But now you have to consider the RL as well as the EA. Okay, so in this full wave drives, you can read again. The current I1 solid flows when the AC waveform of the source voltage is the positive half cycle, and as the CRS S1 and S2 triggered. Similarly, current I2 dash line flows when the waveform of the source voltage are in the negative half cycle. In either half of the cycle, the current will flow in the same direction inside the motor. So this type of operation actually work on two quadrant. I'm going to explain later. Okay, so you have this, and this only works for two quadrant, which is, if I can write that, and we talk about voltage and current. Okay, so current can be positive and negative. If you have this circuit, you can have current positive and negative, and IA is always in that direction. This is IA and constant, continuous. So current flow in that direction. Therefore, you can operate with two quadrant here, quadrant 1 and quadrant 4, right? Because we have Q1, Q2 here, that can also be represented by omega versus top 3. The same characteristic at the top. Right. So what does it mean? This circuit can also have the voltage which is negative. And the average V average equals to, or V out equals to negative value. With respect to that, if you have that VT, VT, so VT, VT can be negative, and VT can be also positive, right? Positive, negative, depending on the alpha. I'm going to show you some simulation just to remind you, just to recap what we did in Powertronics. Okay, so what does it mean? If I bring this to here, okay, just look at this. Okay, just look into the simulation here. So this is, we have the we call this as a rectifier, control rectifier. So in here we have so here we have 4 transistor there, 3. Okay, and to understand the this circuit operation, we just replace the load with a constant current, right? Or here we can have a armature current. Remember, just now we have RL and then the back EMF. So we replace this with a constant current. Okay? Just to look at the behavior of circuit, we replace this with a constant current IA. Okay, so now we're going to simulate the circuit. Okay, so we start with so there is a note here. Positive VDC if when we have a 0 to 90 degree. So if I can, we start with a 30 degree, which is still in between 0 and 90 degree. So alpha here is 30 degree. Now I'm going to simulate the circuit. Look at the circuit, the output voltage. Yeah? So the blue waveform here is actually the output voltage. Okay. So now we have alpha equals to 30 degrees, right? So if you measure from there to there, alpha equals to 30 degree. So if you take the average, you can see that the positive area is more than the negative area, isn't it? So the VT will be positive, isn't it? So now let's increase alpha equals to, so now this is alpha equals to 30 degrees, isn't it? So what about if you have, this is 90 degree. You want to increase alpha up to that point. Let's look at the average output voltage. Okay, I'm going to go back to 30 degree here. I'm going to change to 90 degree. Okay, so now it's 90 degree around the circuit. Look at that. So what happened? If you look closely at 90 degree, if I push properly, this is, if you want to get the average, if you look at the area, the positive area and the negative area is equal, isn't it? They are equal area. So it cancels, isn't it? So therefore, Vt equals to 0 at alpha equals to 90 degree. Yeah? The output voltage equals to 0, the average, because at alpha equals to 90. So remember, we still have a continuous current, flow. What happens if you exceed that 90 degree? Oh, this is wrong. This should be 90 degree. Oh, sorry, 90 degree up to 180 degree. Okay, so let's say we change that to 120 degree. Go beyond 90 degree. Let's try to simulate. Run simulation. Look at that. Now, if you look properly, the negative area here is greater than the positive area. So what does it mean? If you take the average, of course, the average Vt here is negative of something. So it is a negative value. The output voltage is already negative. So if you operate the motor with the alpha from 90 to 180 degree, you will see that the voltage now is no longer positive negative, but it turns out to be negative and positive. Reverse. Vt or Vd here is reverse. So that's why if you talk about the quadrant, okay, if you want to understand it, this is V, this is I, right? Current still flowing in that direction, isn't it? Right? Current still flow in that direction, which is positive, always positive. This area positive, but the voltage Vt can be positive or sorry, you can have positive Vt or you can have negative VT. So that's why it is known as two quadrant operation. So you can operate the conditions whereby you want it to be in quadrant 1 or quadrant 2. Okay? And this is known what? This is known as forward motoring. This is reverse braking. So please refer to the previous note. What is the forward motoring? There is a slide on that. So you can try to simulate. Okay, start from now. Look into the YouTube. There is a lot of examples on the PC simulation on the DC drive. Okay, and compare with my example that I given to you, the circuit that I given to you, and then try to simulate. It's very good to understand the material nodes. Okay, so let's continue. And this is the waveform. You can look into Sharkawi page 171. So I can go to Sharkawi page 171. So here I made some correction in the in the Sharkawi's book. Here it start with a 0. So normally when you want to represent or present the graph or waveform, we need to consider the steady state operation. So here Sharkawi represent start from 0 and start from 0 second. So that's why from the starting point, of course, you don't get a similar waveform, isn't it? So this is different waveform, isn't it? But normally when we try to, so there's some mistake here, I would say. So that should be, I already put in my slide here. I should start with the same waveform there. Start with this waveform. Okay, so again, when you talk about the average voltage, you want to look into the area under the curve. Okay, and therefore if you go through the derivation and finally you find out that the output voltage, the VT, equals to that voltage here, Vmax over pi cos alpha minus cos beta, and this is from the equation, the, uh, the DC drive equation. You have E plus RA I average here. That so there is an equation, sample, examples here. Please go through, right? Example 6.5, and we have example just now, example 6.4. Right? Go and try to understand the example. Please do set 6.4. Then you have example 6.5 as well. Okay. And next, what else? So, and finally, right. So just now we have looked at the half wave waveform, half wave rectifier. So this half wave rectifier only work at first quadrant. And then we look into full wave. So full wave rectifier, control rectifier work for two quadrants, which is Q1 and Q4. But now, how are we going to operate or control the machine such that we have the whole four quadrant control? How is it? So, if you want to have that control that can work for four quadrants, we need to use this known as a dual converter drive. Okay, so dual converter drive, we connect the first on the left hand side here, converter 1 here is a normal full wave rectifier, right? That, and on the right hand side we have converter 2 that works that is connected in anti-parallel. We call it anti-parallel. because the arrangement of this is different, isn't it? This is not parallel connection. If it's a parallel, then you can have that connection here, isn't it? This is parallel, but we talk about anti-parallel, then we have that connection here. Okay, and VA is always in that connection. So remember, alpha, if you have alpha, okay, so let's say we talk about alpha 1, so alpha 1, if you operate alpha 1 from 0, so if you have alpha operate from 0 to 90 degree, we're going to have positive VA, isn't it? But if you operate 90 degree, alpha 180 degree, therefore you're going to operate as a minus VA. So it will change from negative to positive here. Okay. Right. And for converter 2, okay, so for converter 2, again, similar operation. So alpha 2 will have to operate from 0 to 90 degree, then you will get a what? Let's say I put this blue color first. If you operate alpha 2, 0 to 90 degree, you will get this plus minus. Let's say this is VT. I would say VT first, right? VT, isn't it? So positive VT. But if you talk about VA, if you refer to VA, this should be negative VA, isn't it? This is negative VA. And if you operate alpha 2 from 90 degree to 180 degree, so in terms of VT, you are actually operating with the minus VT. We change polarity, and this is equals to VA operation plus VA operation. Okay. So if you have a so current here can work positive current IA, or you can have negative current, just go up there. So this is I, negative current. Okay, so therefore you can operate so you can operate the whole cycles here, the whole quadrant, whereby IA can be positive and negative, and you can also have VT can also positive and negative in all directions. So therefore, you are able to control the machines there in whatever situation is. You can choose if you are in that state, for example. Okay, if you are in this particular state, which is what? Minus VT and minus I. Okay, isn't it? So which one? Which one is that? Should be minus VT. No. VA minus VA, and you operate with a negative current. So that would be that one. That operation is alpha 2 from 0 to 90, and then you have IA reverse. So this converter should operate. Converter number 2 will operate, and you trigger with alpha 2 equals to 0 to 90 degree. Then you have a negative VA, current also flow in that direction. Okay, right. So that's a operation of a single phase dual converter. This is the explain a bit more. Phase control rectifier for quadrant operation. So you have the same single phase supply, and then you have this is Q1, Q4, Q2, Q3. We have discussed that. And look again. Okay, so this is where you have a positive VA, and in the case of constant positive current, so therefore VA should be greater than EG. Remember, you have this back EMF. So VA should be greater than EG, then the current will flow in that direction. And they must flow in that direction. Current will flow in that direction. So in this case, same here. So now the VA is negative voltage. Okay, so negative now. But here you have EG is greater than VA. They are reversed now. So the current flow here, and then EG is greater than VA. So that current will flow in that direction. Then current will flow into that direction. So EG also change the polarity, so that current flow in that direction, and then you have EG is greater than VA. Okay, then we look at this Q1, this is Q4, then we look at Q2 here. So EG should be greater than VA, then you have a current flow in that direction. And then in this motoring, so VA should be greater than EG, but now the polarity has changed, the current has changed, and it goes into that particular direction. So this is a motoring, but in reverse mode. So if you talk about speed, if you have a counterclockwise omega, and you have a torque also in that direction. Okay, sometimes you call it torque E. So here you have reverse direction, omega, and then you have torques in reverse, and here you have speed again, same speed omega, and torque is reverse, torque E, and here you have the same omega is speed is negative, but now you have torque is opposite, torque is positive, so torque. Right? So this is a 4-quadrant operation with a dual converter. Okay, so this 4-quadrant should be in your head. Again, always refer to the other notes, the YouTube that I've shared with you. So this should be in your fingertips now. In your mind, you always have this 4-quadrant operation. It's very important in the DC drive or the electric drive. 4-quadrant operation here. Okay, so if converter 1 operates with a delay angle of alpha 1, the armature voltage is VA 2 V peak over pi cos alpha 1. So again, for alpha 1, we have a positive rate from 0 to pi. So you have a positive VA. So if you operate alpha from pi to 1, so you VA become negative. Okay? So that is the converter 1 operates. And for converter 2, if converter 2 operates with the delay angle alpha 2, the armature voltage is, so talk about that, VA Actually, I'm not. If you talk about VA, if you have alpha there, so we already have VA, the plus minus there, isn't it? So to not to be confused, um, for alpha from, if you operate alpha 2 from 0 to pi, it will produce positive and negative here, isn't it? So that actually equals to negative, yeah? Negative of this value. This is a correct way to represent VA, because you operate from 0 alpha 2 to pi, so you must have negative here, because your VT respect to that converter should be positive, isn't it? So you produce VT here, so therefore VA equals to negative of that particular voltage. Okay, and for full converter, the field voltage is VF to V peak over cos alpha. So for this side, you also have this full converter direct. So that will be the output voltage of VF. So you still can control VF here to control the flux, the IF. Okay, and last but not least, so again, condition for 4 quadrants. Okay. So you can have peak torque, and also you can compare with voltage and current. V out, I out. So that also 1, 2, 3, 4. They are the same. So you can V out, speed, I out, and torque. Right? Okay. So we're going to look at the example for the next video, inshallah. Okay. And do not forget to watch the YouTube on explanation on the, again, on the dual converters drive. Okay. Assalamualaikum.